Yeah, so my video is there, audio is there. Okay. So before starting today's discussion, I would like to correct one thing that I said in the last class. Towards the end, I think I was tired, so I made a mistake there in this problem where this is like previous lecture, end part of the previous lecture. So here there were two walls at same temperature and other two walls at same temperature of 800 Kelvin. So what I said was there will be no heat transfer from 1 to 3, and which is true because the temperatures are same. But that view factor. So this surface is or wall number 1. It views 4, 2, 3 all walls. So therefore, view factor will not be 0.5 in that case. It will be symmetric between 2 to 4, but there will be a non-zero view factor here because view factor is just a geometric property. It's not a it is not dependent on the temperature of the body. So that's why. So I had corrected the explanation, but since the video was by that time it was disconnected, I could not clarify there. So I thought I'll clarify this now. So please take a note that in the last problem where I said this F1 to 3 will be 0, which is not correct. Q1 to 3 is 0 because there is no delta T. So that is true. But due to symmetry, these two will be same, F1 to 2 and F1 to 4. But there will be a non-zero F1 to 3. So that was the correction that I wanted to convey. So after that, we'll go to today's discussion. So today, basically, what we are discussing is the remaining topics from the radiation chapter. Uh, and I think in your assignment there are certain questions which are not completely, you know, you need some extra data for this because I saw assignment number 11. It's due tomorrow, but there also I feel uh, please give some time to note down the solution. Okay. Yeah, I'll take some break in between the questions so that you can note down. That can be done. Or otherwise, you can go back and later also you can see on the YouTube, and maybe there also you'll have the chance to pause the video and see. But anyway, the suggestion is noted down. So basically, today we'll discuss the remaining parts of the radiation chapter. And what that includes is, first of all, uh, this discussion about enclosed gray surfaces. Uh, so that is one topic. Then there are like multiple gray surfaces. One case is two gray surfaces, another case is n gray surfaces. So there are resistances networks like we used to do in conduction and convection steady state problems. Similarly, we can draw resistance networks in radiation problems also under certain assumptions. The primary assumption is it should be a steady state problem, so temperatures should be constant and not changing with time. And along with that, the surfaces should be diffuse, so there should not be any directional dependence in the emissivity, etc. Other properties also. So in that case, one can use resistance network diagram and solve the problems. There are, I mean, professor has discussed those in detail in your class lectures video. Then there is something called as shields, radiation shields. That is very important. We'll also discuss about that. There are two cases in that that we'll discuss. And then there is multimode heat transfer, volumetric absorption. Multimode heat transfer, it's essentially, you should remember that since this is a course, we study each chapter separately. But in practical problems, the problem doesn't know that the radiation is to be studied separately, the conduction is to be studied separately. So all convection, conduction, radiation, all those things simultaneously occur depending on depending on the temperature and the boundary condition as well as your geometry, etc. Sometimes maybe radiation is the dominating one. Sometimes maybe convection is the dominating mode of heat transfer. But nonetheless, there will be more or less in any practical application there will be combination of conduction, convection, and radiation heat transfer modes. So there you consider them in parallel in your resistance network diagram. That is the key. That is the key observation. And then there was a theoretical chapter discussion on volumetric absorption. When typically in the problems that we solve for radiation chapter in this context, we don't consider the effect of medium which is in between the enclosures. That is true because first of all, radiation heat transfer primarily is the what you say, it doesn't need medium for heat transfer basically. But in certain cases, what happens, medium starts participating in the heat transfer. For example, it starts absorbing or reflecting, etc., and that affects your overall energy conservation, etc. But that is, I think, the detailed discussion on that is out of the scope of this course. Professor has just told you about the Beer-Lambert's law. So if you know that much also, it is fine. And if you are interested in higher studies, maybe you can study that in depth. So coming back to that, so we'll start solving some problems because that way I'll be able to clarify most of the things. So let's take first problem. Sorry, before going there, I would like to give you a table which you should all study or revise before studying this chapter, and that is essentially 1 second. Mm, 13.3. So basically, there are certain cases where if you know the formula, you'll quickly solve it. But if you don't, then it takes time. So to avoid that, I thought maybe I'll give you a what you say, table, so that all the essential things necessary for today's discussion will be at the same place. Just let me find it. It should be somewhere here only. Yeah. So for diffuse diffuse gray two surface enclosures so I'm giving it for two surface because that is easy to start with, but it is not like that it is only valid for two surfaces. When there are n surfaces, you can individually apply these formulas between any two surfaces. So first is long, or sometimes they are also called as infinite parallel plates. So this is the case typically studied in this radiation shield, etc. So that is the first case. Typically you'll have one plate like this and another plate like this. So we denote them by number 1 and 2. Maybe I'll use alphabet A for this, otherwise some may get confused. So plate 1 will have area A1, epsilon is emissivity of the plate, and temperature T1. And second plate will also have similar properties which are relevant for radiation heat transfer. So here typically, since they are very long, we assume that the area is same, and F12 and F21 both are equal to 1, because whatever energy leaves from 1 goes to 2. We assume that the side losses are negligible, and whatever leaves from 2 goes to 1, assuming negligible losses from the sides, since they are very long tubes or plates. And in that case, your heat transfer from 1 to 2 is nothing but you know you can draw the resistances, right? So for example, what I mean is there will be one surface resistance, there will be one what you call shape resistance, and then the final there will be one uh, surface resistance again because of the emissivity. So first resistance will be 1 minus epsilon 1 by A into epsilon 1, and due to the shape factor or shape, the resistance will be 1 by A into F12. I can write A1, but since we are taking A1 and A2 equal to A, I am just writing it A. And then again there will be a surface resistance which will be a function of emissivity of the second plate. So typically from our thermal resistance network analogy, we know that this will be T1 power 4 minus T2 power 4 divided by total resistance. Now total resistance will be 1 minus epsilon A epsilon 1 plus 1 by A F1 to 2 plus 1 minus E2 A epsilon 2. And here F1 to 2 is 1. So this is 1. And you can take A common from the all the three terms in the denominator and take it to the numerator. So what remains is sigma A T1 power 4 minus T2 power 4 divided by 1 minus epsilon 1 by epsilon 1 plus 1 minus epsilon 2 by epsilon 2. And if you simplify further, it simplifies as the numerator remains same, denominator gets simplified as 1 by epsilon 1 plus 1 by epsilon 2 minus 1. Okay, and this is a standard result. You should remember this because we will use this in our discussion on the radiation shields also. So in that case, what happens? Between the two parallel plates, you put multiple sheets or metallic plates only, but they'll have different emissivities than the plates, or then like their own surfaces will have different emissivities from one side as compared to other. So all those cases will be there, but essentially the discussion starts from this derivation, and this was done in the class also, but still I thought we'll do it again here. So this is for a long infinite parallel plate that you should remember. And then the second case is long, or in some cases they are also called as infinitely long or infinite concentric cylinders. So what happens? First case was only like flat plates, but there will be certain cases where you'll have concentric cylinders. I think one of your assignment problems is also like this. There, shield is put along a circular cylindrical tube or pipe or something like that. So here maybe I'll draw it, but like don't take it the drawing very seriously. I just want to show two concentric cylinders here. So there will be one cylinder, and then it will be enclosed by another cylinder. We will have something like this. Yeah. And inner cylinder will have radius R1, outer will be having R2, radius of the cylinders. So in this case, we'll number the inner cylinder as 1, outer cylinder as 2. So here also what you know is F11 is 1 because it's a convex surface, so it won't intercept the radiation energy emitting from itself. And therefore F12 will be, no sorry, F11 will be 0 because like that, and therefore due to the addition principle or addition theorem, F12 will be 1. and then you can apply similar, resistance network and simplify the case. But in this case, what happens? Hmm. Yeah, and like we'll solve some problems, and there you'll need this equation, so I'll derive it here only. And due to reciprocity theorem, we know that A1 into F12 will be equal to A2 into F21, right? Therefore, F21 will be A1 by A2 into F12. F12 is 1, so this is essentially A1 by A2. And what is A1 by A2? A1 is the surface area, curved surface area of the cylinder. So that will be pi dl, and both cylinders have same length typically. So therefore, it will essentially be R1 by R2. So therefore, F21 will be R1 by R2. Remember this also, because you know in some cases you will directly use it. And F22 will be 1 minus F21 because of the additional principle. I should have boxed the whole thing together, because these are two important results you should remember. Okay, so that is about the shape factors for this case. Other than that, if you draw the resistance network, mm, like what we did in case of infinite parallel plates, sorry, there will be again three resistances, two due to the surface and one due to the shape of the geometry. So this one will be 1 minus epsilon 1 A1 epsilon 1. This will be A1 F12. F12 is 1, so therefore I am writing it, so I can just write it as A1. This will be epsilon 2 by A2 epsilon 2. See, compare it with the previous case where it was only a parallel plates. So here we assume that the area will be same. But in case of concentric cylinders, you cannot assume A1 equal to A2, right? Because the radius are different. So therefore, your Q1 to 2 will be nothing but sigma T14 minus T24. That remains as it is. And you have to, take all resistance terms in the denominator and sum it up. So you'll get something like this. Now, what is done to further simplify this is you just take A1 common, and then it goes to numerator. So 1 by A1 is taken as common from the denominator. So other terms remain common or same in the numerator. But what you end up at the denominator is 1 minus epsilon 1 plus 1 plus A1 by A2 into 1 minus epsilon 2 by epsilon 2. I hope this is not confusing. It's just a simple manipulation. And then this, if you separate this fraction into two terms, this one will get cancelled, and therefore you'll end up with Q1 to 2 as sigma A1 T1 to the power 4 minus T to the power 4 divided by 1 by epsilon 1 plus 1 minus 2 by epsilon 2 into A1 by A2. And we have seen that A1 by A2 is nothing but R1 by R2. So you can put that here and you will get the final relation. So you should remember two things here. At the numerator, there is a A1 term, not A2, because otherwise, you have to take F21 in the denominator, and this expression is not correct in that case. So, okay, I'll just write the expression and I'll highlight the important terms. This one will be R1 by R2. So, remember, this is A1 here, or maybe I will put a star mark here, or maybe 1 second, different color would be better. Okay, no, where is red? is fine. So one change is A1 is here and you have this R1 by R2 ratio. So you should remember these two terms here. And then there is a third case. Maybe I'll highlight or leave it, or maybe I'll do that. Okay. So then there is third case, which is concentric spheres. So first case was infinitely long flat plates. Then there is a case which is infinitely long cylinders, concentric cylinders, and then in some problems they will give you it as a concentric sphere. So in that case, I will not do the complete derivation, but the only thing that changes is if let's say this is a 2D cross section of the sphere, because you can't view the sphere in 3D in this paper. If this is the inner sphere is named as 1 and outer is 2, here we know that F11 is 0, which implies F12 as 1, correct? This is same as the cylinder case, and then you do the same, you draw same conclusions, but at the end you'll get you'll get this term, right? This A1 by A2, and in this case it is, since it's a sphere, area is proportional to the square of the radius, so nothing changes, the formula is same. T to power 4 divided by 1 by epsilon 1 plus 1 minus epsilon 2 into R1 by R2 whole square. So this is the only difference here, and here A1 is nothing but 2 pi R1 into length of the cylinder. If it is given, take it as take the value, otherwise you can calculate it as per meter, but here A1 will be 4 pi R1 square. So A1 is there, but here you should note down the difference, that it's a square, not just a first power. Okay, so this is regarding the spherical concentric spheres case. Okay, and then there is a final case that is also important, which is called as small convex object in a large enclosure. So you must have seen some problems in which they mention that a small ball is hanging in a big room, and in that case, what is the rate of heat transfer from the ball to the room, assuming ball is hot? Some type of problems are there. So let's say this is your bigger enclosure and you have a very small convex object here. This is the object 1 and this is your big enclosure 2. So similarly, A1, T1 and epsilon 1 are the area, temperature and emissivity of the small convex object 1, and for room it will be a large room, so this area will be very much bigger than the object area, surface area. So here also nothing changes, you write the same expression, you take the A1 common, but in this case what happens, here also F11 will be 0, so the derivation goes in the same direction. But in the end, what you end up with is you have this formula, right? Sigma A1 T1 power 4 minus T2 power 4 divided by 1 by epsilon 1 plus 1 minus epsilon 2 by epsilon 2 into A1 by A2, right? So here, since A2 is pretty much larger than A1, A1 by A2 is very small value and we consider it as to be 0, approaching 0, and therefore what happens, your Q12 is essentially sigma epsilon 1 A1 into T1 power 4 minus T2 power 4. So your formula simplifies. here because the area ratio is pretty much small. So these 4 cases are important. You should remember this. Maybe I'll highlight this one also. This is the important case here. Yeah. So do you need some time to copy this or should I go ahead? Maybe I'll put this next page. I think this is the last page, right? Maybe this one is. See, I think some of you might know this already, but it is important to mention it here because most of the problems that we'll solve, they are revolving around these concepts only. So it is essential to clarify them in the beginning itself, so that the next problems we can solve fast. So that is the whole idea here. So yeah, shall I stop or move?
Go ahead, sir. Complete it.
Okay. So remember these 4 cases. The problems will be revolving around similar to that. Similarly. I mean, maybe combination of 2 or something like that. But essentially, will revolve in these 4 cases only. So apart from that, yeah, 1 second. We'll take a problem here. Let me just see. Okay, I want to take simple problem so that we'll take the shields and then the resistance networks later. Let me just see. Okay, so based on what we have discussed so far, maybe we can take this problem. Let me just once read it. Okay, so the question is okay. So these are 3 concentric cylinders. 1, 2, and 3. Diameter of each cylinder is given in the problem. So the inner cylinder, which is the smallest cylinder, is having diameter of 150 mm. The middle one is of 20 or 250 mm, and the biggest is I think 350 yes, 350 mm. So I'll just note down what all given information is there. These are 3 concentric long cylinders. Okay. And apart from the diameter, temperature of the inner cylinder is given as 80 Kelvin. Middle cylinder is unknown, and the outer cylinder temperature is 300 Kelvin. So basically your outer cylinder is hot and inner cylinder is cold. So there will be heat transfer from 3 to 1 because of the temperature difference. And the emissivities of these surfaces are given as epsilon 1 as 0.05, epsilon 2 as 0.1, and epsilon 3 as 0.2. And I'm not writing it, but they are, you know, what you say, they are diffuse surfaces, diffuse gray surfaces. So we have to find under steady state under steady state, what is the temperature achieved by cylinder 2. So basically T2 is what is the question. So now first of all, these are cylinders. You should take note of this. So now we discussed, right? We have to go to the second case, right? Because these are long cylinders, and we know we did the derivation. So if there are only two cylinders, we know that we can calculate the heat interaction using this formula, right? But here there are three cylinders and intermediate cylinder temperature is unknown. So what we can do, we can consider two cylinders together. So what I mean is, if you want to draw the, what you say, thermal resistance network, so it will look like this. So basically if this is if this is the surface of your cylinder 1, then since we are we are interested in heat transfer from 3 to 1, right? So we don't consider what is happening inside the sphere. We are pretty much interested in what is happening from the outer surface of sphere 1 till the inner surfaces of the sphere cylinder 3. So therefore there will be one what you say, surface resistance that will be like this. Then there will be one shape resistance which will look like this. That will be 1 by A1 into F12. And then there will be another surface resistance due to the emissivity of second cylinder. So this will be your boundary of your second cylinder, right? And then between 2 to 3 there will be again three resistances. I hope this is clear what I am drawing here. And then this will be your boundary of cylinder 3. This will be 1 minus epsilon 2 A2 epsilon 2, 1 by A2 F23, and 1 minus epsilon 3 A3 epsilon 3. Okay, so this is the resistance network. I am not drawing the whole cylinder area. I just draw cross section and I showed. Okay, so now consider two together. So if you consider these two together and these two together, what you get is Q122. What is our formula for long concentric cylinders? You have A1 or the inner cylinder area at the numerator, and then R1 by R2. So that ratio is also there. So here you can write sigma A1 T1 power 4 T2 power 4 divided by 1 by epsilon 1 minus epsilon 2 into R1 by R2, right? And A1 is nothing but 2 pi R1 into L. Here L is not given, so we'll divide everything in terms of heat transfer per unit length. That also is possible. So on similar lines between 2 to 3, what you can write? It's just that replace 1 by 2 and 2 by 3 in our formula. So you will end up with sigma A2 T2 power 4 T3 power 4 1 by epsilon 2 plus 1 minus epsilon 3 into R2 by R3, right? Correct, no? So now, and here A2 will be 2 pi R2 into L. So what we do is, like it is mentioned in the problem that we need to find T2 in steady state. So in steady state, Q12 per unit length, if you take it like this, will be equal to heat transfer between 2 to 3 per unit length. I am just taking per unit length because I don't want to write L in the expressions, because anyway we are going to cancel it anyway. So if you do that, what you end up is sigma A1 is 2 pi R1 T1 power 4 T2 power 4 1 by epsilon 1 epsilon 2 term R1 by R2. This will be equal to sigma 2 pi R2 T2 power 4 T3 power 4 1 by epsilon 2 1 minus epsilon 3 divided by epsilon 3 into R2 by R3, right? So now this sigma gets cancelled because it's a constant. 2 pi also gets cancelled. Now we have this equation, and everything is known. All the terms mentioned here are known except T2. So the only unknown in this equation is T2, which is here and here. So we have one equation, one unknown, and you can solve it, right? So I'm not going into the details here because that will take another 5-10 minutes if I just put everything here and keep on writing. I give you the homework, maybe you can consider it as just plug in these values because all the values are mentioned here. The data is already given. So you have to just plug them in and get the T2 value. And one thing you should note here is these all temperatures must be in Kelvin. This was told in last class also, and in radiation chapter anyway, everywhere you just put Kelvin only. So if you solve this, I can simplify. For example, just for the sake of simplicity, let some constant C1 be equal to or leave it, I mean, no needed. So you can solve this, and on solving we should get T2 as 282.14 Kelvin. I am not solving it here because I think it's just a exercise for proper usage of calculator and values, etc. So I leave it up to you, and you should get this answer. Okay. So I think I'll stop for a couple of minutes so that you can copy this. If you have any doubt, you can type it out or ask also. Similar problem can be framed with, instead of cylinders, I can put spheres and then ask you to find the temperature of the middle cylinder or outer cylinder, whatever. So this is a problem with cylinders, but I can frame the same question with spheres also. And you just have to, this R1 by R2 term will have R1 by R2 whole square in that case. So just keep that in mind and you'll be fine. Okay. Just let me know when should I start next question. I'll wait for some time so that you can note down if you want. So shall we start the next question? This is like a simpler version of it, but still, I mean, if you don't know this that ABCD formula, you can't solve these questions that easily in the exam. It will take a lot of time basically. So that is the case. Yeah. So shall we start the next question? Yeah, I'll go ahead. If you have anything, let me know. I'll come back. So then there is another version of this type of questions. For example, in this problem, there are two concentric spheres.
Hello, sir.
Yeah.
You are not looking into the chat boxes at all, sir.
Oh, acha. Sorry. Chat box was open, but the new messages they were coming, but my screen was not getting updated. Now I scrolled. Okay. Sorry. Yeah. Look into the last problem, assignment 11. Last problem, huh? Yeah.
Yes, sir.
I know you. I think you asked me this problem in the last class also. We'll solve this.
Yes, sir.
Just hold on. I'll take one problem with the simple case, then we'll go into the radiation shield, etc. There, in the end, we'll do this. This is a problem involving re-radiating shield surfaces, which is also called as insulated surface. We'll solve this. Don't worry. I know that. I remember that you had asked about it. So before going to the next things, we'll just take one problem with the sphere. So these are two concentric is it the spelling? No. Concentric spheres. So you have one sphere like this and another sphere. And it is mentioned that the inner sphere is at 700 Kelvin. 700 Kelvin. And outer sphere is at 400 Kelvin. And D1 is 0.3 meter. Diameter is basically diameter of the sphere. And outer one has diameter of 0.8 meter. And then the emissivity of the sphere one outer surface is given as 0.5. And emissivity of second or outer sphere but inner surface emissivity is 0.7. So basically I'll write the sentence here because that's important. It is mentioned that the inner surface emissivity or inner and outer surface emissivities for outer sphere are 0.7 and 0.35 respectively. So this is the new thing in this problem. Otherwise, it's a straightforward problem. But in this problem, what they have mentioned is this outer sphere, which is denoted by 2 in the figure. Its inner surface has different emissivity and outer surface has different emissivity. So you have to be careful here. And yeah, so we can write therefore epsilon 2 inner surface. I will use this symbol epsilon 2i for inner as 0.7 and emissivity of surface 2 but outer surface we'll use the symbol epsilon 2o as 0.35. Okay. Then it is mentioned that ambient temperature is 30 degrees Celsius. So this all information is given in the problem, and then it is asked that determine the net radiation heat transfer between the spheres and also find the convective heat transfer coefficient at the outer surface of sphere 2. So this is a two-part problem. First is you need to find the radiation heat transfer, net radiation heat transfer between the spheres, and then you need to find what is the heat transfer coefficient, convective heat transfer coefficient on the outside of sphere 2. So this is a problem where two modes of heat transfer are also considered. So for the first part, nothing changes basically because we have Q1 to 2 as sigma A1 T1 power 4 T2 power 4 divided by 1 by epsilon 1 plus 1 minus epsilon 2 divided by epsilon 2 into R1 by R2 whole square. So this R1 by R2 is nothing but D1 by D2. Because if you take ratio of radius and diameter, it will be same. But here the trick is this epsilon 2, there are two values, right? So in the problem they have given two values for the emissivity of the second sphere. So when you are considering between spheres 1 and 2, we are considering essentially heat transfer in this area, right? Or in this vacuum or whatever the fluid is there. So therefore we have to consider epsilon 2i for these calculations. So therefore this will be epsilon 2i. Okay. So and a1 is nothing but 4 pi r square, r1 square. Correct. So now everything is known. Sigma is 5.67 into 10 to the power minus 8. and this epsilon 1 is also given as 0.5, epsilon 2 inner surface is 0.7, r1 r2 is radius ratio, so that will be 0.3 by 0.8, or 0.15. So if you plug in all these constants or this information, you should get the value as 1669.3 watt. I'm not doing the calculation because that will take time and we can use that time for some other good problems. So I leave this verification to you. You can cross verify by putting the values, and you should get the answer as 1669.3 watt. So that is the first. Now coming back to the second problem. So what they are asking is, if this is your outer surface of sphere 2, they are asking, you know, this ambient temperature is 30 degrees Celsius, which is 303 Kelvin. So there is heat transfer due to radiation also, because they have given emissivity at the outer surface of sphere 2. And then there is heat transfer due to convection also, because there is a significant temperature difference between the outer sphere, which is at T2 is at 400 Kelvin.
400 Kelvin.
Yeah. So now in this case, you have to consider both. So we know that in steady state, Q12, which is the heat transfer rate between sphere 1 and 2, will be equal to Q convection from sphere to outer surface and Q radiation, right? That is what your energy balance tells. What will be your Q convection? It will be H A2 into T2 minus T ambient. And what will be the radiation heat transfer here? It will be sigma and epsilon A, so A2 epsilon 2 outer into T2 power 4 minus T ambient power 4. Okay, so note that this is the outer surface emissivity, because the radiation transfer, heat transfer is now taking from the outer surface of the outer sphere to the ambient. So therefore this will be epsilon 2 O. So now, and what will be the A2? A2 will be 4 pi R2 square. So here everything is known except H, because Q12 we calculated this 1669.3, and all other things are known. So if you plug these values and calculate H, you should get H as 5.05 watt per meter square. And since this H value is very small, you can also infer that this is nothing but a case of natural convection, because in forced convection, the H value will be of the orders of 100 or more than that. But since it's only 5, most likely it's a natural convection happening from the hot spherical surface to the cold ambient. Okay, so I'm not doing the calculation. I request you to cross check it and let me know if I have done some mistake. So I think that is about the basic cases. So shall we move ahead for the problems on radiation shield and re-radiating surfaces, etc.? Yeah. So this is this. Now we'll go to the important thing, which is radiation shields. So typically, like most of the problems in this domain are typically for flat shields. So you'll have two flat plates, infinitely long or very long, and then you need to put some shields to reduce the radiation heat loss between the two plates. Typically in furnaces and in nuclear reactors or wherever there is a high temperature on one side of the plate, and you want to reduce the temperature in a smallest with smallest space possible and smallest complications without complex changes. In that case, shields are used. So most of the problems will be flat plate case, but as your assignment is there will be certain cases when you put shields, cylindrical shields over long cylinders also, and in some cases you can put shields over a sphere also. But those problems are less common. The more common problems are where you have a flat plate and then you put flat sheets in between. So regarding that, we'll take two cases because that will cover most of the variation of problems that you'll see across. The first case is, which is famous or favorite for objective type of questions like GATE exam or ESE prelims or CSE prelims, something like that. So, CSE prelims will not have technical, sorry. So, the case will be two long flat plates with n number of shields in between and plates and shields have same emissivities. Let's say epsilon. So this is one case, and second case happens where your shields will have different emissivity. So again, you'll have long flat plates with n number of shields in between, but your plates and shields will have different emissivities. So these two cases are there. So basically, your emissivity of plate will not be equal to your emissivity of shield. This is also common, less common case, but yeah, you should know about this. So this whole thing boils down to the resistance network because we typically assume steady state condition for solving such problems. So we'll take first case, or maybe I'll number it so that. So we'll take the first case. So here you'll have something like this, arrangement something like this. So this will be your first plate, second plate. So if you don't have any plates or anything between, what do you have? Q12 without shields. We did that right at the start of the class. So it will be sigma A T1 power 4 minus T2 power 4 divided by 1 by epsilon 1 plus 1 by epsilon 2 minus 1. So this is your standard results, right? That we got in the first, at the beginning of the class. Yeah. But what happens when you put a shield? For example, if you put one shield like this, the shield, it adds its own surface resistances, right? And they will be, let's say if this is your shield A, so you'll have 1 minus epsilon A by A into epsilon A, 1 minus epsilon A by epsilon A. So basically, when you add a shield, there are addition of two resistances and one more this space resistance is added, which will be 1 by A of shield A between A to 2. Maybe I should not have used the symbol A here because that is confusing with the area. Maybe I'll change it. So let's say I use small a symbol for a shield, denoting the shield. So epsilon A into A, capital A into small a. Same resistance will be added on the other side, assuming the shield has same emissivities on the both side. And then this will be from A to 2, shape factor from A to 2. So what happens when you add a shield? Basically, three resistances are added. Okay. So first case, consider emissivity 1, emissivity 2, and emissivity of plate. Oh, sorry, not plate. Shield has some same value, which is epsilon. In that case, what happens? Your Q1 to 2 without shield or shields, it simplifies to T1 power 4 minus T2 power 4 divided by, so 1 minus epsilon 1 or epsilon 2. So this is nothing but 2 by epsilon minus 1. So it becomes like this. Okay, so this is your equation 1, or maybe we'll use some Roman numericals. Okay, I hope this part is clear. And let's say you add one sheet or one shield. In that case, what happens if you add one shield? This will be your shield. So let's say A. Then the resistance network looks like this. So instead of 3 resistances, now you have 6 resistances. Okay. So this will be 1 minus epsilon A epsilon 1 by A into 1, because F1 to A will be 1, right? So this will be into 1. This will be 1 minus epsilon A epsilon 1 minus epsilon A epsilon. This will be again A into F A2, small a2. So that will be again equal to 1. And then you'll have same. So basically, if you add, so Q12 with one shield is equal to sigma A T1 power 4 minus T2 power 4. And what is the total resistance? So you can see there are 4 same terms here, right? So we can add them. So what you get is 4 into 1 minus epsilon divided by epsilon, because the A goes to the top. And then there are 2 terms, with 1 by A. So there will be 2 here. Okay. I hope this is clear. I just skipped one step where you take A common and then put it in the numerator, but this is also fine. So if you further simplify this, what you end up getting is 4 into 1 by epsilon minus 1 plus 2. Okay. Yeah. So this is sigma A T1 power 4 minus T2 power 4 divided by 4 into 1 by epsilon minus 2. So what I can do, I can take sigma A T1 power 4 T2 power 4. This remains same. I can take 2 common, right? and what I remain inside the bracket is 2 epsilon minus 1. So let's say this is your equation number 2. So now compare one equation, which is this equation, and this equation. So what you observe here is you basically end up Q12 with one shield is equal to Q122 without shield divided by 2. So by just putting one shield of same emissivity, your rate of heat transfer from plate 1 to 2 has reduced by half. And if you add third sheet, I give you it as an exercise, you'll observe it that Q1 to 2 with two shields, it comes out, or maybe I should write similarly, Q1 to 2 without any shield divided by 3. And it is intuitive also, right? Because what will happen, you'll add one more sheet like this in between, so these 3 resistances will again be there, then here it will be 6, and then when you take the difference, this factor will become 3. So therefore it looks like this. You can try. I encourage you to try that. That will make it clear. And therefore there is a famous general formula, Q1 to 2 with some n number of shields is equal to Q1 to 2 without any shield divided by n plus 1. So you should remember this, and sometimes in problems directly you have to use it. Okay, so there are, like, this is one case. Okay, so we are in this case. So keep in mind that the emissivities are all same here. Then only you get a simple formula like this, which you have to remember. And this is for same plate and shield emissivities. Okay, so then I can frame two type of questions here. First question is, I will give you T1 and T2. So let's say T1 I will give you as some 1000 Kelvin, T2 as let's say some 500 Kelvin, and then I will ask you that if let's say two shields are put in between the plates 1 and 2, what will be the rate of heat transfer between 1 and 2? That is one type of question. So you can calculate without any shield and just divide by 3, which is n plus 1 is 3. Then you'll get Q1 to 2 with shields. That is one set of problem. Another variation of this question is, I will ask similarly, like same, I will give you the temperatures of plates as some values, and I will ask that reduction of 75% heat transfer due to radiation is expected. Then how many shields of same emissivity need to put in between the plates. So this is the second variation of the problem. Okay, so here you don't even need the temperatures, because what is given is Q122 with N shields compared to heat transfer without any shield is nothing but equal to 75% reduction is expected, right? So the actual heat transfer will be only 25% of what it used to be. So it will be 25 by 100, or it will be 0.25. And we know that if you look at this formula, which is the derivation we have got it, if you take this numerator in the denominator here, you'll get the same term, right, which is here. So therefore basically this has to be equated to 1 by n plus 1. Therefore your n plus 1 becomes 4, and then you need to put 3 shields. Okay, so that is another variation. I am not taking problems for each case because we don't have that much time here, but I just want to tell you what all can be asked so that you will be prepared. And then there will be a last variation that uh, you know Q122 will be known, T1 will be known, let's say some 1000 Kelvin or something like that. Emissivity is known, and then find T2 with, let's say, n equal to 4 shields. So basically now I am playing with the temperature. So far I played with the number of shields, which is n. Then I played with the Q. So what will be the Q after putting 4 shields? Something like that, knowing T1 and T2. Now there can be a third variation of the problem where you don't know one of the temperatures, but you know the heat transfer rate, and you know how many shields you have put in. So that can be a third variation of the problem. You may want to take some time for understanding this. That is fine. Please let me know if you have any doubts. Otherwise we'll go to the next case. So like there can be many problems from this, okay? And if you have seen any previous year GATE questions, you'll realize that if you know this formula for flat plates at least, you'll be fine. This formula I'm talking about. Okay, so now we'll go to the last category of problems, which is regarding the let's say 3-body interaction or 4-body interaction. Then there are something called as re-radiating surfaces. So re-radiating surfaces is nothing but I'll just mention it here. So this is the end of this flat radiation shields. Sorry, before moving on, the second case, this case where your emissivities will not be equal. What happens in that case? So in that case, you need to solve the resistance network individually. So basically, uh, there is no simple formula for such cases. You have to draw the resistance network and then calculate all the resistances and solve. In some problems, what happens? They say that this emissivity and this emissivity. So basically, the plate emissivities are same, but the emissivities of all the shields that will be in between, they are also same, but not same as the plates. So, for example, uh, you know, so for example, epsilon 1 and epsilon 2 will be equal to, so these epsilon 1 and epsilon 2 will be equal to 0.5, but for the shields, the all emissivities will be 0.7, something like that. So in that case also you can simplify, because then all your resistances will be same, na? The resistances associated with the shields will be same, because they have same emissivities. So that is also a simple case, but I'm talking of a case where each plate has different emissivities and they are not equal to the plates. In that case, you can't do anything. You have to solve the resistance network individually. So I hope that is clear. There is a problem where plate emissivities are same, but shield emissivities are different. But all shield emissivities are same. But we don't have that much time here, so I'm skipping it. But you can also think about that variation of problem, and maybe it will be beneficial if you come across such case later. So other than that, now let's go to the final topic, which is about enclosures, more than two enclosures, straight enclosures. I think this curved and all are not in the syllabus, like curved enclosures, etc. Flat enclosures with re-radiating surfaces. So there is something called as re-radiating surface. Okay, so first of all, it is characterized by no heat transfer across that surface. So for problem solving, you should remember that if any surface is re-radiating surfaces, or sometimes they call it insulated surface also. If that is the case, insulated, so we all know, because insulation means that there is no heat transfer. But in some cases, they just mention re-radiating surfaces. In that case also, there is no heat transfer. You should remember. So what typically re-radiating surfaces is, it will be well insulated on one side. So you'll put some suitable insulation covering on one side of the surface, and convection effects are negligible on the opposite side which is radiating. So this is a definition of it. If you want to know, you can keep in your mind. If you don't, that is also fine. But you should remember at least this, that there is no heat transfer across it. So we'll take the problem. I think 11th this last problem of your assignment. I know it's due tomorrow, but anyway, some bonus for attending my class. You can take it as that. So typically there will be some enclosure. Here it is a equilateral triangle kind of enclosure. So this is the question, and width of all sides equal to 1 meter. This is your first, second and third surfaces. T1 is 1000 Kelvin and epsilon 1 is 0.33. T2 is given as 700 Kelvin, emissivity is 0.5, and this guy is your insulated surface, right? Insulated surface with temperature which is unknown. Area is, I think, these areas will be same only because this is equilateral triangle, right? Duct, but it will have same length and same dimension, so areas will be same. And emissivity is given as 0.8. Okay. So yeah, they are asking per unit length. So determine net radiation transfer from surface A1 per unit length. Okay, so I hope from the class discussion lecture you may have idea how to draw the resistance network for this type of geometries. So essentially, I'll draw it slightly bigger so that you'll have enough space to show the resistances. And before solving this, maybe here I'll write. Let A1, A2, A3 be equal to A, because it's an equilateral triangle and length is also same, so area will be same. And also, before moving further, as we discussed in the last class when we discussed shape factors, here it is equilateral triangle, right? And shape factor is a geometric property. It doesn't depend on the temperatures. So therefore, whatever energy is coming from 1 to 2 and 1 to 3, they will be same. Therefore, and due to symmetry, F1 to 2 will be equal to F1 to 3. And we know F11 will be 0 because it's a flat flat surface, right? So F11 will be 0. And another thing is F11 plus F12 plus F13 is equal to 1. So, this guy is 0. So, and these two are same. So, from these two, you get F12 and F13 will be equal to 0.5. And similarly, if you apply this same logic to second surface and third surface, you will get F23 equal to F21 equal to 0.5 and F31 and F32 equal to 0.5. Remember, this is only possible because this is an equilateral triangle. If this is not an equilateral triangle, you have to solve it using the reciprocity, etc., etc., or maybe using some charts or something like that. But here it is a simple solution because it's an equilateral triangle and 50% of the energy from one surface goes to the not energy, but like geometry wise, area wise, one surface is 50% of the other surface, another surface, you know I mean, if you want to like look at it, one will see 50% of the two and 50% of the three, like that. So this one you should be aware of because this will be required to solve the problems. Now this is your first surface, second surface and third surface, and for this guy it is 0. Q is 0. It's insulated or re-radiating surface. So then you draw the surface resistances, right? So they will be like this. So this will be 1 minus epsilon 2 by A epsilon 2. This will be 1 minus epsilon 3 by A epsilon 3. And this guy will be 1 minus epsilon 1 divided by A epsilon 1. So these are resistances due to the surface characteristics, and that is represented by the emissivity. If it is a black body, then epsilon is 1, right? So in case of black body, there is no surface resistance. There is only shape resistance. Then the shape resistance will be like this, because these three bodies are seeing each other, right? So there will be a triangle like this. So like this. Okay. And this is, this resistance is between 1 and 2. So I can write it as 1 by A1 into F12. And since A1 is equal to A, I'm just writing it as A. Similarly, I can write this as A into F13, or, you know, uh, yeah, I mean, that is fine. And this also, the shape resistance will be also 1 by A into F2 to 3. And we already know all these things, right? F2 to 3 is known, 1 to 3 is known, 1 to 2 is known. So, and the correct way to show this is, this will be your EB1, because you assume that, it's a black body. So this will be your first node. And then due to its surface properties, it's not the black body. It's basically by this point, which is called as J1, it essentially becomes a gray surface, not a black surface anymore. Then you have this surface resistances, etc. Something like this. And then again, this will be your J2 and J3. And third surface also is not black. It has some emissivity. So that will be, and now here it will be EB3. Okay. And similarly, this guy will be, yeah, so this will be your EB2. Okay. And this will be your surface characteristics, because of the emissivity of the second surface. And since we know the all shape factors are 0.5, we can put 0.5 everywhere in the shape resistances. So this becomes 0.5 times A. This also becomes 0.5 times of A. This also becomes 0.5 times of A. Okay. And again, we can further simplify, because here width of the side is 1 meter, and anyway they are asking us to calculate per unit length. Therefore, area is nothing but 1 meter square. Okay. I mean, assuming per unit length, right? So, I mean, you get my point, right? Anyway, like leave it. We'll just, because if you simplify here itself, no, it will be very easy to solve the problem. Anyway, before going there, let's say T1 is 1000 Kelvin, right? T2 is given as 700 Kelvin. So basically, the heat transfer will be in this direction, because T1 is higher and T2 is lower. This will be the direction of your Q1 to 2. This is your radiating surface, so there will be no heat transfer across this node. So what will happen is, typically the heat will come from here and it will go like this. So this will be your Q1 to 3, and this will be your Q3 to 2, and they will be same. Then only there will be no heat transfer across the third surface. Okay.
Sir, that depends upon the temperature of the third surface, right, sir?
Yeah. So that is actually, see, in this problem it is not asked. In this problem only they are asking what is the heat transfer from first surface.
But how can we say only it is from 1 to 3? Why can't it be 3 from 3 to 1? If the temperature of T3 may be somewhat high.
How can it be high? You tell me. If let's say this is something like 200 Kelvin or something, okay, then there will be heat transfer in this direction and in
No,
this
no.
direction.
229, yes, sir.
Correct, no? But okay, that is also possible. Whatever it is, okay, let's say we assume certain temperature, let's say T3, okay, which is unknown at this point, and we assume this direction, it may be wrong. What will happen if the actual direction of heat transfer is in this direction from 3 to 1, then whatever we solve, and at the end that
to make it
Q1
negative value.
will get negative value. So,
Negative value, yes.
That is okay. I mean, I don't want to, like what you are thinking is also correct. So if that is the correct thing, then Q1 through will be negative and Q32 will be positive. So we have to solve that, and we'll see what happens.
Okay.
So I hope you understood so far what we are doing.
Yes, sir.
Yeah. So now the thing is, in any case, we'll assume T3 as some temperature, but
one more doubt, sir. Is there any chance of following the heat from 2 to 3 also?
2 to 3. Yeah, so that is represented by this, no? This Q32. If there is a heat transfer in this direction, whatever we solve, this value will come negative.
Negative, okay.
Yeah, so whatever, like we don't know at this point from where to where heat is flowing. So we assume certain direction.
Okay.
And we'll solve assuming that direction, and whatever values we get, according to that, we will revise the directions. That is how it should be. Okay, so we'll go to the next part. So here, see, we need to find in this problem, we need to find what is the value of Q122, right? This is or Q122 plus Q123. What is heat leaving from 1 to 3 and 1 to 2? So
determine the net radiation heat transfer from the surface 1.
Yeah, so from surface 1, heat is going to 2 as well as 3, according to this assumption of directions. If you had assumed some other setup, then in case you have to see which direction. But this is simple, na? We have to just add 1 to 2 and 1 to 3. But now the question is how to find them. So, just 1 second, I am just looking at the problem. Okay, so now consider from 1 to 2. So how many resistances we have? So let's say this is your EB1, black body emissivity or black body, something like that. Sorry. So this will be, what is 1 minus epsilon 1? Epsilon 1 is given as 0.33. So this is 1 minus, and I think we can take area as 1, no, because the side is length 1 and we want per unit length, right? So we'll take A as 1 meter square. So in that case, what is your first resistance? That is 1 minus 0.33 divided by 0.33, and this will be your J1. This is basically 2 by 3 by 1 by 3, so it will be 2, approximately 2, but let it be. Then we'll have this resistance, which is 1 by 0.5 because A is 1. Then you arrive at J2, and then you go to the T2. So this is your T1 at 1000 Kelvin, and this guy is at 700 Kelvin. And what is the resistance, surface resistance here? It will be 1 minus epsilon 2 by epsilon 2. So epsilon 2 is given as 0.5. So 1 minus 0.5 by 0.5, it will be 1. Okay. And now across this, sorry. So this will be your J3, and these all are 0.5, 1 by 0.5, right? Because all shape factors are 0.5 there. And the emissivity of third guy is 0.8. So 1 minus 0.8 divided by 0.8. So that is 0.2 by 0.8. So that is 1 by 4, 0.25. Okay. And then you'll have this, whatever temperature this body is at, consider it at that temperature and like that. But the thing is Q3 is 0. So there is no heat transfer through this body. So what will happen? You can neglect this surface for the calculation purpose. So this part,
Sir, one more doubt. Sir, because of insulation, you are physically saying that Q3 equal to 0 for the third surface. But what about the two surfaces, sir, 1 and 2? There may be chance of heat transfer outside also.
No, this is enclosed. So yeah, there can be chance of heat transfer from outer surface. So basically what you are asking is this, right?
You are specifically saying that Q equal to 0 here, right?
So you are saying heat transfer happen from these two surfaces, right? Yeah, it will happen. But
purposefully he has given insulation. That's why you are saying it is Q equal to 0 here.
Yes. Yeah. So basically, I think what is happening is there is some heat source here, which is heating this one surface, and then there is some heat sink. So heat will go from here to that heat sink. So we don't know what is outside this enclosure. So we can't.
No, we are not considering that part.
See, we solved this problem, this sphere problem before. So here also we initially solved what is inside. We calculated what is your Q1 to 2, and then we looked at what is happening outside. So in this problem also something like that can be there, but they have not mentioned it, so we can't comment on that. So here the note is, or the trick is, since there is no heat transfer from third point or third surface, this surface resistance doesn't play role in Q1 to 2, right? And therefore we can neglect it. So essentially it becomes like this. This is your 1. This is your resistance 2. This is 1 by 0.5 is again 2. And this is 1. And this is your second point. And then you have two resistances which are connected in series to each other but parallel to the main circuit. So something like this. This is also 2. This is also 2. I hope this is clear, because there is no heat transfer between this leg, otherwise Q3 cannot be equal to 0. So therefore now you have to solve. So this circuit is equivalent to, we know in series the resistances add up. So this will be again 2, and this will become 4 in parallel to the 2. And this other outside will be same, 2 and 1. So this is your second point, this is your first point. So now 1 by 2 and So one like this, sorry. Yeah, so these are your J1, J2 points, just for the sake of somebody should not get confused. So now you have resistance 2 and 4 in parallel. So what will be the effective resistance? 1 by 2 plus 1 by 4. That will be 6 by 8. So effectively it will be 8 by 6. So this remains as it is. This becomes 4 by 3. This is 1. And maybe I'll write it inside, otherwise it's confusing. And this is equivalent to this. Yeah, 1 by 2 plus 1 by 4, 6 by 8, 8 by 6, 4 by 3. So when you add them up, what is your... So 3 plus 4 by 3. So 3 plus 4 by 3 is 13 by 3. So this is a total heat, total resistance. So we know it is sigma, and we are considering area as 1, T1 power 4, T2 power 4 divided by total resistance, which is 13 by 4. Oh, 13 by 3. 4, 1 by 4 plus 1 by 2. Yeah. So if you do this calculation, I have the numbers, I'll give you. Maybe you can cross check whether it's correct or not. So this first term, which is sigma T1 power 4, because we know T1, right, and sigma also know. So basically the final answer I'll give, because the sigma T power 4 I have, so that will be confusing. So essentially you should get 9874 watt per meter. Is it there in the option? Yeah, so this is your first option. Yeah, 9942. Maybe you can cross check it once, but it's close. Maybe it should be around 9800 something. Maybe you can cross check once the calculation. Otherwise, I'll do it if you want. So maybe I can do it just to make sure that we are not doing anything wrong. So it is 5.67 into 10 to the power minus 8 into, what is your T1? 1000 power 4 minus 700 power 4. Array. Divided by 13 divided by 3. Yeah, it is 9942.99. Is it coming because we assume this as 2? Because it is basically 0.67 divided by 0.33. So it is 2.03. I'm not sure how much difference will it make. So basically it is, if you divide 13 by 3, you get 4.33, right? So you add, you add 0.03, 4.36. Okay, let me check. 5.363. Okay, so 4.363, 5.67 into 10 to the power minus 8 into 1000 raised to 4 minus 700
Sir,
raised to 4. 1 second.
sir,
Yeah, I understood why we are not getting 999. The reason is,
the third surface MCT also given 0.8.
yeah, let it be.
So
Just
we may need to think that surface
no,
resistance also into account.
no, because it's not. See, consider this as a electric network. So if you have connected any point in electric network to the ground, that wire will have its resistance, but no current will flow through it, right? Or if
Okay,
it
okay, yes.
here actually it's not exactly 2, it is 2.03. Our first resistance, this resistance, because it is 0.67 divided by 0.33, right? So that is why
Yes, sir.
the answer is not matching. But if you do, 1 second, so it should be 0.3, and then your final resistance will be 4.363. So if you put that, you should get the answer. See, here we are dealing with the power 4 now. Therefore, even if you make small mistake, your calculations will go very abruptly wrong. So this is what it was asked in the question, but we'll go one step further and we'll find what is T3, because that is what is confusing everyone, right? And
Yes, sir.
to find T3, the only thing that we have is, since it is a steady state condition, in that case this Q13 and Q32 will have to be equal. Then only T3 will be constant, right? Otherwise it will not be a constant. So therefore,
Yes, sir.
to find T3, we have Q13 equal to Q32 under steady state. So now you can write the expression for Q13. So that will be, uh, 1 second. EB3 minus J1, EB3 minus J2. In this case, what will be Q13 and what will be Q32? So whatever heat is coming from 1 to 3, it will flow from EB3 to J3 and then to EB3, right? EB3 to J1, EB3 to J2. Yeah, so basically what you have to do is here, see, one way is to solve whole thing like that, like we solved for Q12, right? So you can solve for similar procedure for 1-3, similar procedure for 3-2, and then finally equal them. But that is a complex process. It will be slightly complex. So simple process is, see, whatever heat is flowing through 3 to 2, the same heat will flow from this branch also, and this branch also, right? So you can consider only up to J2. No need to consider the last leg. And similarly, from 1 to 3, whatever heat is flowing, it follows this path, right? And through this path. So like that. You understood?
Hmm.
1 second. J1 minus 3 to 2. One second. Radiation balance. We have to do heat balance. So consider this. So consider your J3. So there is J1, J2, J3, and this is your EB3, right? So under steady state at J3, heat in must be equal to heat out, right? Then only its temperature will be constant. So what is the heat coming in here? So you can consider only this much resistance, right? So this will be 1 by 0.5, 1 by 0.5, and this is 1 by, or this is directly 0.25. And this is actually 2 only, 1 by 0.5 not needed. The resistances are actually 2. So you have to balance these quantities. So whatever is the direction for this guy, you need to balance it out. So how do you do that? In case of electrical analogy, you divide the current, right, and then you write it is by voltage by R. So here your Q1 to 3 which is coming, and Q3 to 2 is going, and Q, let's say this is your Q3 dash or something like that, is equal to 0, right? This is your Q3 to 2. This is your Q1 to 3. Okay, I hope this is fine. So if you do this, if you do the radiation energy balance on this J3 node, okay, what is Q1 to 3? It is nothing but J1 minus J3 divided by 2. What is Q3 to 2? It is nothing but J3 minus J2 divided by 2. And what is this Q3 dash? Is nothing but J3 minus EB3 divided by 0.5. One second, actually I am getting confused here because how should I say this? Okay, let's say if you assume these directions and if you equate it to 0, but that will make J3 as 0, correct? So there will be no heat flux flowing from the yeah, I mean sorry, see, there should not be any heat flux flowing from J3 to AB3, right? Because here it has to be 0. So basically energy balance at J3 node gives you that whatever is coming, the heat should go out, right? And then what is Q13? From this diagram, it is J1 minus J3 by resistance, which is 2. And what is Q32? That is J3 minus J2 by 2, which is the resistance. And therefore, if you put that, so Q13 is J1 minus J3 by 2. This is your first term in your energy balance. Minus Q32 is J3 minus J2 by 2 equal to 0. Therefore, your J3 is nothing but average of these two. Then only this will be 0, right? Yeah. It is mentioned that it is EB3. Okay, so now the question is, what is J2 and J3? See here, I mean, J3 is equal to EB3. Yeah, so actually, there is no need to draw this third leg, okay, because anyway it is 0, no? See, there is no need to write this because there is no heat transfer from there. So this essentially is equal to your EB3 here, and that is equal to sigma T3 power 4, because there is no resistance between J3 and EB3 because there is no heat transfer flowing. So the note is here, and I also got confused there. Since the third area is adiabatic or pre-radiating, your J3 should be equal to your EB3. Therefore, the value of epsilon 3, which is the emissivity of third surface, is of no influence on T3. This is the case. Actually, they have given you this epsilon 3 to confuse you. In this problem, this epsilon 3 doesn't have any effect on your T3 because there is no heat transfer across from J3 to E3, right? Otherwise, this Q3 equal to 0 is not satisfied. And therefore, you have to assume in this problem or any other problem where you have radiating surface, there you have to assume at the radiating node your J3 is nothing but EB3. So ideally you should not write it as EB3, you should just write it as you should not write it as G3, just write it as EB3, but we follow that convention, so this is what we should write. And I think now we can solve the problem. Yeah, actually I myself got confused because so you know, therefore sigma T3 power 4 is nothing but J1 plus J2 by 2. So now question is how to find J1 and J2. So we know that, you know, EB1 and J1 is like this. There is resistance of 0.23 in between them. So, and we also know what is the Q 1 to 2, we just calculated it, right, in the previous section of the problem. So therefore Q1 to 2 is nothing but EB1 minus J1 by 2.03, which is the resistance. So we know QB1 as 9874, right? This is known, 9874. This you have to calculate from sigma T1 power 4. T1 is known, right? So this is sigma into 1000 power 4, and therefore you should get J1. And J1 you should get approximately 36653 watt per meter. Okay. And on the same lines, you need to find J2, right? So take the last leg. So there here resistance is 1. So I'm talking about this last part. 1 second. So this leg. So here again Q1 to 2 is flowing, right? So again Q1 to 2 is nothing but J2 minus EB2 divided by the resistance, which is 1. And this is nothing but sigma into 700 power 4. And this is same as 9874. Therefore, if you solve this, you should get J2 as 23488. Yeah, the unit is watt per meter square, yeah, because it's sigma T power 4, right? Sorry. So that's how we calculate J1 and J2. And then you put that, we know that sigma T3 power 2 is J1 plus J2 by 2, right? So we have to add 36653 plus 23488 and divide them by 2. If you do this, I'll do it. 36653 plus 23488, which is 60,000 something. And if you divide it, you get 30070.5. Now you divide it by the Stephen Boltzmann's constant. Okay, so 30070.5 divided by 5.67 into 10 to the power minus 8. And you need to take the fourth root of this guy. So if you do the calculation, finally you should get 853.4 Kelvin. So now I think you'll be satisfied. So the temperature comes out to be 853 Kelvin, so which is in between 1000 and 700, right? So therefore, whatever directions we assumed, they turned out to be correct. But I encourage you to assume some other direction and solve the problem. You should get the negative values for Q23 and Q13, and that's how you can solve this problem. Okay. So shall we stop for today?
Yes, sir.
Yeah. Okay. I think we overstretched it, but yeah, I think we'll stop. If you have go through this, like, do you need some time to write it down, or it's fine, or shall we close?
No, completed, sir. No, completed, sir.
Okay then. Yeah. So we'll stop for today and see you in the next class. Okay. Yeah.
Thank you, sir. Thank you very much. Good night.
Good night.